All right, let's review what we know about catalysts. We talked about how catalysts speed up a reaction. So that is the hallmark of a catalyst, is that it speeds up a reaction. Now, biological catalysts are referred to as enzymes, but they essentially function the same way. They increase the rate of a reaction. So, what does that do to activation energy and to the rate constant, etc.? Well, a catalyst lowers the activation energy. Remember, that's the barrier that a reaction must go over, or the threshold energy that it must meet in order for a reaction to occur. Basically, it just lowers that hill. It makes the hill easier to get over. So what happens to the rate constant is that it increases, therefore it also increases the rate. All right, so let's compare what an uncatalyzed reaction might look like in terms of its mechanism as compared with a reaction that is catalyzed. So if a reaction is uncatalyzed, this might be its mechanism, that A plus B react together to form a product, but it has a relatively large activation energy, therefore its rate is pretty slow. It's a pretty low rate. Well, what if I took the same reaction and just added a catalyst to it? That fundamentally changes the mechanism. Notice in this case, it's just one step. This is called an elementary reaction. But in this case, it's two steps in which the first step, the reactant A, attaches to the catalyst to form what we call C, in this case is an intermediate. Then C ends up reacting with B to form the product in the catalyst again. So something I want to highlight here is that the catalyst starts off in the reaction and ends in the reaction. Therefore, if I'm going to determine what the overall balanced reaction is, the catalyst and C both get crossed out, and so the overall reaction is just A plus B makes the product. So it doesn't end up in the overall balanced reaction because it doesn't get consumed in the reaction. It gets used and then spit back out exactly as it was before. So the catalyst changes the mechanism or the pathway the reaction goes through, but isn't at all consumed in the reaction. So the 3 points to summarize what we just said is that a catalyst speeds up the forward and reverse reactions. So it lowers the the energy of the transition state. Second, a catalyst lowers the activation energy. While lowering the activation energy, it ends up changing the mechanism. It goes through a different path to achieve the product. And then last, the catalyst is not consumed. So you want to remember these 3 features of a catalyst. Now, in terms of its physical interaction, what types of catalysts are employed in reactions? There are homogeneous catalysts and heterogeneous catalysts. So in a homogeneous catalysis reaction, a homogeneous catalyst is one that's in the same phase. So same phase, say the reactants are aqueous, they're dissolved in a solvent. That means the catalyst is also dissolved in a solvent. Let's say that the reactant is gas, then that means that the catalyst is also in the gas phase as well. So a homogeneous catalyst just means that they're in the same phase. A heterogeneous catalyst, on the other hand, means that they are in different phases. So you might have a catalyst that is a solid, and then you might have a reactant that is a gas. Okay, so this just, the heterogeneous and homogeneous catalysis just refers to the phase that the catalyst and the reactants are existing inside. So last, we want to look at the function of biological catalysts. So a biological catalyst, as we already referred to, is called an enzyme. An enzyme is a biological catalyst. An enzyme is different than a non-biological catalyst because it is a protein. It is composed of amino acids, all tethered together, tied together, bonded together, and then it wraps up into this pretty complex molecule. There are two definitions we have to be familiar with before we explain how an enzyme functions. And the first definition that we need to be familiar with is active site. What is an active site? The active site is the area of the enzyme that actually performs the catalysis. It's responsible for catalyzing a reaction. The second definition that we need to be familiar with is the definition of a substrate. The substrate is really like the reactant. It is what is interacting with the active site. So the substrate is like your reactant. Put that underneath here. And it is what is binding to the active site of the enzyme. All right, there's a couple of different models to explain how an enzyme and a substrate interact with each other. This is a more antiquated model. It's referred to as the lock and key model, which suggests that an enzyme has basically a perfect opening for a substrate, like a lock and a key. So the enzyme would be the lock and the substrate would be the key, and they perfectly fit into this little area. And when they bind together, the reaction is able to be catalyzed, and then the substrate changes into the product and is released from the enzyme. The more up-to-date and accurate version of how a substrate and enzyme interact is that the substrate doesn't necessarily fit perfectly, but does have an attraction to this active site. And when the substrate comes into contact, the enzyme changes its shape. It molds its shape, and then it's able to catalyze the reaction, and then the substrate forms the product. So this is called the induced fit model, and this is the more up-to-date version of how a substrate and enzyme interact with each other. So let's take all that we've talked about in terms of catalysts and answer this question. Example question 1. If a reaction goes through a one-step process when uncatalyzed and a two-step process when catalyzed, with the second step being the RDS, rate determining step, draw a reaction energy diagram for both curves on one set of axes. All right, so I'm going to first just draw my axes. Let's do that line. Great. So I have two little straight lines. Oops. All right, let's label these axes. So here, put energy, and on the x-axis is progress, so reaction progress. So let's first draw the uncatalyzed reaction, and we'll draw it in blue. So blue will equal uncatalyzed. Right, the uncatalyzed reaction is a one-step process, and no matter if you have a catalyzed reaction or uncatalyzed, they both will either be endo or exothermic. So this tells you that the overall reaction is exothermic. So it may look like this. All right, with the reactants here, the products here, and this is our delta, oops, not delta, this is our EA. And this right here, the gap between the reactants and products are our delta H. It's our delta H value. So notice products are lower than the reactants, which makes delta H a negative. Okay, let's draw the catalyzed reaction. We'll draw it in green. So the catalyzed reaction is a two-step process, and the second step is the RDS. So maybe it's something like this. Okay, so notice that the activation energy is definitely lower here than it is for the uncatalyzed reaction. This is 2 steps, which means I have 2 hills. The second step is the highest, so this is my rate determining step. So I'm just going to label this EA2. This is EA1. And this is my RDS. All of these are transition states at the top of each hill. Transition state. And notice the transition states for the catalyzed reaction are lower in energy than the transition state for the uncatalyzed reaction. All right, so we have finished up chapter 16. Let me know if you have any questions.